we present BIEVR-LIO, robust LiDAR-Inertial Odometry, through bump image-enhanced voxel maps. We introduce a novel map representation to capture fine-grained geometric details to improve the robustness of LiDAR-Inertial Odometry in environments with sparse or uninformative geometry. Inside each voxel, we iteratively calculate a dominant plane using point covariance. Based on the footprint of the voxel corners on this plane, we define a local image coordinate system with pixels of 5 centimeters. Each incoming LiDAR point is then projected onto its voxel's oriented image plane. We accumulate a high-resolution height image of the local surface across multiple scans. The point's height above the plane is stored in the corresponding pixels using a distance-weighted averaging scheme. By only storing the deviation from the dominant plane per pixel, BIEVR encodes rich 3D geometry in a compact 2D image at high resolution without assuming any specific geometric primitive. This allows us to store the subtle details efficiently. The BIEVR representation can directly be used for scan-to-map registration. We minimize the difference between each input point's height above the image plane and the stored pixel value. The resulting Jacobians combine a normal direction term similar to point-to-plane ICP, with 2 additional gradient directions from the height image, which provide constraints in directions that are unobservable under a classical point-to-plane optimization. For the registration, we also introduce a map-informed dual-resolution sampling scheme. Based on the mean image distance, we approximate the amount of geometric detail stored in each voxel. We then sample more points inside the voxels with the highest score that contain relevant geometric constraints. In unstructured environments, the map-informed sampling selects high-density points in geometrically distinct areas. In structured environments, the map-informed sampling implicitly selects high-density points on edges and corners without explicitly defined heuristics on those features. We test our approach on a variety of geometrically challenging environments where all other tested geometry-based approaches diverge. Thanks to the combination of our high-resolution map representation and the map-informed sampling, our approach can exploit subtle geometric details as relevant constraints in the registration and achieves accurate odometry despite the largely uninformative geometry. We also demonstrate that our approach runs in real-time onboard robotic hardware, and that the BIEVR representation can also be used for downstream tasks. In this experiment, we use the BIEVR map for elevation mapping. The quadruped then uses the elevation map to plan its footsteps during perceptive locomotion. You can find our code online. Thanks for watching.